Hi students, welcome to this video where we're going to be solving the problem of kinematics in two dimensions. I want to invite you to subscribe to our channel so you can just get notifications of all the new videos we're going to be recording about physics and mathematics. In this problem, they say that a great kangaroo can bound across level ground with each jump carrying it 10 meters from the takeoff point. Typically, the kangaroo leaves the ground at 20-degree angle. If this is so, what it is its takeoff speed and what is its maximum height above the ground. So basically, we have a problem of kinematics in two dimensions, as I mentioned. So it's a problem of projectiles, uh, so similar to a problem of a projectile, right? So what we know the range, right? There is 10 meters, and we know the angle of the initial velocity because the kangaroo will be leaving the ground at 20-degree angle. So we're going to be working with equations in both dimensions, in the x dimension and in the y dimension, equations of kinematics, and then what we have common for both will be just the time, right? Will be the time. So the time is common, is the connection between the equations in the x direction and the equation in the y direction. So what we know when we are working in a problem like this one, you know that it's just pretty similar to a projective problem. We know that the highest point on the trajectory, at the maximum height, uh, the velocity would be equal to the initial velocity, so it would be equal to b sub 0 cosine of 20 degree, and it would be pointing to the right. And we know that by, the velocity in y, would be the vector 0, so will be equal to 0. So we have no velocity in the y direction. So if we know this right now, we can just using equations of kinematics try to solve the problem. So we know that at the highest point in the trajectory, where b final y is equal to 0, so the vy is equal to 0, we can use this equation to say that b final y equals to b initial y, right, minus gt1. I will call this time t1, because will be the time needed to reach the maximum height. So we know that this b final y, that would be basically the velocity at the highest point in the y direction, would be 0. So we get b sub 0 y is equal to gt1. B sub 0 y would be b sub 0 sine of the angle, so it would be b sub 0 sine of 20 degree, right, equals to gt1. So I can just solve for b sub 0, and I can say that b sub 0 would be gt1 divided by the sine of 20 degree. I will just keep this equation as equation 1. I will use this equation later. So now I know that in the x direction we have uniform motion, so there is no acceleration in the x direction of the motion of the kangaroo, right? So we know that the variation in position, that is basically in this case the range, the variation in position along the x-axis, that is the range, will be equal to b sub 0x times the time of flight. So we'll call this time t2 because t2 will be the time of flight, so the total time on the air, while this t1 is just time for maximum height. So there are different times, right? So I know the range, okay? I know that b sub 0x would be b sub 0 cosine of the angle, so cosine of 20 degree times t2, but we know that t2 will be equal to t1, to 2 times t1, sorry, because we don't have a resistance here. And the time of flight will be equals to 2 times the time for the maximum height. So if I replace b sub 0 by this expression that I call equation 1, and I replace t2 by 2 times t1, right? We can say here, you know, that the range will be equal to gt1 over the sine of 20 degree times 2t1, right? Of course, we have cosine of 20 degree here because b sub 0 is gt1 over sine of 20. So we have time cosine of 20 degree. There is this factor over here that I didn't include. So let me erase. So I have here cosine of 20 degree times 2 times t1. Cosine of 20 over sine of 20 would be cotangent of 20, so the range would be this case, you know, 2 times g t1 square, because t1 times t1 would be t1 square, cotangent of 20 degree. So we know the range, as I said, we know the angle, we know the acceleration of gravity, we are ready to find t1. So we can say that t1 will be the square root, right, of the range of the attacks divided by, and then here in the denominator we have 2g cotangent of 20 degree. So you substitute, right, and you say that the range is 10 meters, right? And this is 2 times 9.8 meters per second square, cotangent of 20 degree. This would be 0.43 seconds. Well, with this now, with this time t1, we're ready to find b sub 0. So we can say, you know, that b sub 0, what is g t1 over the sine of 20 degree would be 9.8 meters per second square times 0.43, 0.43 second. 0.43 seconds divided by the sine of 20 degree. So b sub 0 would be, in this case, 12.3 meters per second, what is approximately 12 meters per second. In the second part, they ask you to find the maximum height above the ground. To find this maximum height above the ground, right, we are going to now use another expression. Let me then just delete or erase this part over here to the left to have a space, you know, to solve it. So we want to find delta y, so the maximum height. So I know for this second part that one of the equations of kinematics, state that y is equals to y sub 0 plus b sub 0 y times t1, minus 1 over 2 g t1 square. In this case, right, we can bring y sub 0 to a left, so we can say that this is h, the height, or delta y. So you can say that this is delta y. There is the same that h, and will be b sub 0 y t1 minus 1 over 2 g t1 squared. I'm using t1 because t1, the time 1, is the time needed to reach the maximum height, right? So when I substitute, I get that delta y is equal to 12 meters per second is the y component, so is sine of 20 degree times the time, that is 0.43 seconds, minus 1 over 2 times 9.8 meters per second square times 0.43 seconds square. So you can find delta y like that, and you will get, in this case, the delta y would be approximately 0.86 meters, or just 0.9 meters. And we have solved the problem. So we found the takeoff speed. The takeoff speed was 12 meters per second, and the maximum height above the ground was 0.9 meters. Thank you for the attention. I hope the problem will be useful for you to understand this topic of projectiles, kinematics into dimension. And I invite you again to subscribe to our YouTube channel so you can get notifications about every new video that we are going to be recording. Thank you for your attention.